Hello everyone. On behalf of the organizing committee of Cellular Automata India, I, Sukanta, welcome you to the second day of the webinar series, Understanding Reversibility, Edward Fredkin Memorial Lectures. In our first day, we had two very interesting sessions. The first talk was delivered by Professor Sushmita Shurkole of Indian Statistical Institute, Kolkata, on logic synthesis methods for reversible and quantum circuits. In the second session, Professor Kenichi Morita of Hiroshima University presented on time reversible symmetries in reversible cellular automata and their applications. Those who could not join last time, they may see the video lectures in Cellular Automata India YouTube channel. Today we have two sessions, Asynchronism and Reversibility and Introspection from Cellular Automata perspective, followed by Information Mechanics then and now. Our first speaker is Dr. Sukanta Das, who is a founding member of Cellular Automata India and also the organizer of the ongoing webinar series. Dr. Dash is an associate professor of the Department of Information Technology of Indian Institute of Engineering Science and Technology, Shibpur. He is one of the leading researchers in cellular automata theory and applications. Currently, he is exploring the computational abilities of cellular automata, the non-uniform cellular automata, partial number conservation in cellular automata, chaos and randomness in cellular automata, interconnection of logic and algebra with cellular automata, democracy, computation, and cellular automata technology. Apart from research and academics, he is also an active member of the All India Science and Rationalist Organization, IIEST. We request Professor Dash to take over the session. Over to you, sir.
Thank you, Sukanta, for your introduction. Let me give few seconds to share my screen. Is my screen visible?
Yes.
Thank you again, once again, Sukanta, for your introduction, and good afternoon, everyone who are present in this webinar. As Sukanta mentioned, that my title of my talk is Asynchronism and Reversibility and Introspection from Cellular Automata perspective. Let us start with this word called asynchronism. What is this? So asynchronism is an antonym of synchronism, and by synchronism we understand that components of such a system are bound to act based on some common agreement. That is, whenever we talk about a synchronous system, it is having several components, several elements, they will act, but they are bound to follow some agreement. They have to act based on some agreement. Since the elements cannot work based on their wish, so sometimes we see synchronous systems as disciplined one. So we observe that synchronous systems are disciplined. Here, no member is allowed to go as you like. Take an example. Solar system is an example of synchronous system. So all the elements of solar system, they are very disciplined, and the planets, they cannot act based on their wish. Another system we can see, then army march, is very known to us, very common thing is known to us. Army march is also another example of synchronism. You can see that the all the soldiers, they have to act based on some agreement. The soldiers cannot act based on their wish. So this is another example uh, of a synchronous system. Now question is, how can we reach to such an agreement? So most common way to reach an agreement is to use of a clock. So this actually introduces the concept of a global clock or central clock, by which all components of a synchronous system, they agree to act. Now, then what is asynchronism and asynchronous system? Take an example first. Say a fish market in India, an example of asynchronous system, and who have experience in this fish market. See, they're the customers, the buyers and sellers. They can run by their own rule sometime, and they can go at any shop. The customers can go at any shop, and they can shout. The buyers also can do several things. So this is an example of asynchronous system, and it shows that asynchronism allows some kind of independence, allows independence of elements. Now the question is, if independence is allowed, then sometimes we observe, we say that, okay, this system cannot be disciplined. So from that point of view, I want to ask this question: can asynchronous systems achieve the goals of synchronous systems? As I've said, they're not disciplined. If you consider that asynchronous systems are not disciplined, or to be disciplined, the system has to be synchronous, then the goal achieved by synchronous system, the same can that same be achieved by asynchronous system? Let us ask this question. I want to use another term here. The term is political term, the democracy. So this democracy is also associated with asynchronism. In case of a democratic system, the elements, the members of the system can have the freedom of speech. They can you know uh, 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 they can opine, etc. So like this, not that like the march of army, where everyone has to follow some direction, exact one direction everyone has to follow. So the question is, see, does independence of elements hinder a system to achieve a goal? In other words, if this kind of independence is given in a democratic system, can democratic system achieve the goal what an autocratic system can do? In this talk, we shall introspect this question. We shall inquire this question through reversibility. Now, what is reversibility? Reversibility is a phenomenon which allows the system to go back in reverse direction without losing information. As we know from physics, that there's no loss of information during evolution, right? So if I can go forward, since there is no loss of information, I can go also backward. At least I can trace the back uniquely. And we know from the physics that microscopic world exhibits reversibility. Okay, and when a system moves from one state to other state, then I can consider that some function is being used. And from mathematics, from mathematical point of view, that transition function is to be bijective. So because we know the bijective function, for the bijective function, we can have an inverse. And if I go from one state to other state, following one function, by applying the inverse one, I can come back my original position. So the function, the transition function, is to be bijective. Yeah, it's really a strange property. As I've said, that reversibility is a property of a system which allows you to go forward as well as go backward. And there is no loss of information. You can trace your history uniquely. So it's a strange property, and synchronicity actually helps a system to be reversible. So the question is, yeah, it's all right. Synchronicity helps system to be reversible, but whether it is mandatory that the system is to be system is to be synchronous to be reversible, that is our that is the question. Take a snapshot of solar system again. If you consider a solar system in isolation, then you can see there is a reversible behavior is there. So, for example, from the using the orbit of of a planet, so of Earth, you can trace the previous state also. So where from it has come, you can trace that one. So in isolation, if you take the solar system, yeah, you can see some kind of reversibility. You can find some kind of reversibility here. And I was saying that microscopic world exhibits reversibility. So in atomic structure also, we can find this reversible phenomenon. And mathematically, the function which transforms the system from one configuration or one position to other position, that is to be bijective. So I have shown one example of bijective function. Say f is a bijective function. Here you can see from A, by applying function f, you can go to 3. And if you want, from 3, you can come back to A if you apply f inverse. So you can uniquely come back. So therefore, when you're talking about reversible systems, the associated function is to be a bijective function. Now the question is, can an asynchronous system be reversible? So we shall introspect this question through cellular automata. Cellular automata is actually, they are nature-inspired model of computation where time and space both are discrete. So space is partitioned, it is divided into small pieces, and we call that small piece a cell. So it's like this. So suppose the space is there, three-dimensional space. It is partitioned, small cubes. So we are calling the small cube as a cell. So the cells are arranged as a regular network. You can see in the left-hand side, the cells are arranged as regular network. A cell can interact with its neighbors only. So there, a system may have many cells, but a cell cannot directly interact with everyone. It can interact only with, with its neighbors. So in the right-hand side, you can see that there is a green cell, green cube. It's a green cell. There are some red cells. So so the green cell can see the states of the red cells only. That is, the green cell can interact with the red cells only, but not all. And after seeing what it can do, it can perform a teeny computation. And interestingly, and cellular automata, all the cells act synchronously. That is, all the cells, they simultaneously look at their neighbors and they perform teeny computation, and and it goes on. So it is a synchronous system. However, although the cells can perform very little computation, they are having very little computing ability, but when they act together, they can exhibit some beautiful behavior, complex behavior. So just a small simulation, how it can show how it can generate some complex pattern and show complex behavior. So let me recall Edward Fredkin. Edward Fredkin is a computer scientist and physicist who died in last year, and this webinar series is dedicated to his memory. So Edward Fredkin believed that universe is a big cellular automaton. It is his belief. We don't know whether really the universe is a cellular automaton or not. We don't know. But at least one thing we can claim here, that cellular automata, they are really a nature-inspired model of computation, and Cellular Automata can model many natural phenomena, physical phenomena efficiently and effectively. Okay. So let us move to the next point. It is asynchronous Cellular Automata. So as I was mentioning that Cellular Automata is by definition classical, it is synchronous, but we can make it asynchronous also. Asynchronous means there is no clock, there is no central rule which enforce all the cells to be updated simultaneously. It means in asynchronous Cellular Automata, the cells are allowed to act independently. So now question is, how can we model that independence? See, Cellular Automata, they're the mathematical model. Okay, so mathematical model. The question is, well, how can we model that independence property? So this is one solution is we can use probabilistic update of cells. In case of synchronous Cellular Automata, the all cells are updated deterministically. As I have said, all the cells are updated simultaneously. So determinism is there. But here, to model the independence, let us do some probabilistic update. And there are two popular probabilistic update you'll find in literature. One is fully asynchronous update. In fully asynchronous update, a cell from the whole set of cells is chosen uniformly and randomly at each time step, and that is updated. Okay, so at each discrete time, exactly one cell is chosen for update, and that choice is done uniformly at random. This is one way of implementing, the independence. Other popular ways called alpha synchronous update, where each cell is given a probability is alpha. So this alpha means the probable, chance of updating the cell is alpha. It implies that the chance that cell will remain in its old state is 1 minus alpha. So in this way, all cells are updated, right? So these are two popular ways, of implementing independence of cells. Now, in my talk, we have some consideration. Firstly, in my talk, I shall consider one-dimensional cellular automata. The first example I have given three-dimensional, but I shall not consider three-dimensional again. Although the results I'm going to show, they will have, many of them will be applicable for others also. But we shall consider only one-dimensional cellular automata, and we shall consider finite cellular automata. So that is, number of cells are finite. I can put on one note here that classically cellular automata, they are defined over infinite lattice size. So number of cells are infinite in classically it's considered. But here I shall consider finite cellular automata, and we shall consider periodic boundary condition. It is like this. Say all the cells, they're arranged like this: cell 0, cell 1, cell n-1. The cell 0 and cell n-1 are two extreme cells. They are neighbor of each other, as if the cells form a circular array. So this is a periodic boundary condition. So that is, I'm having I'm considering a cellular automata which are having n number of cells, where n is a natural number. Further, we shall use ECA rules for the cells. ECA rules are binary rules. That is, the cells can have only in two states, 0 and 1, and a cell can depend only on left neighbor and right neighbor. So three neighborhood dependency is there. So we shall use ECA rules, to show the reversibility in asynchronous cellular automata. Generally, ECA rules are presented in tabular form. So it's like this. So as I've said, it is a three neighborhood dependency. A cell depends on itself and on left neighbor and right neighbor. So there are three states of the cells. Since I'm considering binary system only, so my state of my can be my one state can be the cell's one state can be 0, left cell can be 0, right cell can be 0. So 000 is one combination. Similarly, 001, 010, up to 111. So 8 possible combinations I can see for, for one cell, right? And for each combination, I can have some different value, transition value. So 000 to 0, 001 to 1, etc. So therefore, I can represent a function in this fashion in tabular format. So you can see here that I have written one function. So 10101010 is a particular function. It's an 8-bit string. If I represent in tabular format, I can have an 8-bit string. And sometimes this 8-bit string, it is remembered as by its decimal equivalent. So it's the given 10101010. It is equivalent to number 170. So we sometimes call it 170. So by 170, by the number 170, we mean a particular rule or particular transition function. So I've given two examples. One is 170, other is 38. Anyway, so in this system, I can have to the power 3, 256 number of rules. Property of cellular automata, automaton is each and every cell, they follow the single rule, right? Each and every cell, they follow a single rule. Therefore, if I am having 256 number of rules, I can have 256 number of cell automata under this condition. That is binary, cell, binary state, and one cell depends on left neighbor and right neighbor. So under this condition, I can have 256 number of cellular automata. Now let us see with this, take one example of 170. And if I apply fully asynchronous update, if I apply alpha synchronous update, and if I apply synchronous update, what are the difference? How they will act? So take rule 170. See, I'm given one example. So I have started my system from 0001, this configuration. So we call this one configuration. So 0001. So my system, my cell automaton starts from this one, 0001. And suppose I am first applying fully asynchronous update. So as I have said, the fully asynchronous update is exactly one cell is chosen uniformly at random for update. Suppose the red mark cell is chosen, right? In this particular case, I think you can see my mouse pointer here. So rightmost cell here, which is marked as red, it is chosen for update. So therefore, I have to update this, and so I am applying rule 170. In this case, my local configuration is like 010. See, 0010, this one. So if I come back to my table, 010, I can get here 0. 010, I can get here 0. So this 1 is replaced by 0. This is for fully asynchronous update. Okay. Now come to this alpha synchronous update. Suppose middle two cells are chosen for update. See, if the first red cell is chosen, it is 000. For rule 170, 000 is 0. So it remains at 0. And for the next red cell, it is 001. And 001, you can see here in the table that 001 is 1 actually. So the second red 0, second red 0, it becomes 1. So if I apply alpha synchronous update on the same rule, I can have 0011 as my new configuration. Finally, if I apply synchronous update, synchronous means all the cells are updated. So then if I start from 0001, I'll get 0010. So you observe I'm using same local rule, same rule 170, and same I have started from same configuration, but depending on the update, right, I may reach to different configurations. So this is just an example how the way of update affects the dynamics of system. Now come back to our reversibility issue. If I consider a finite system and finite cellular automaton, then I can observe that all the configurations are cyclic. That is, all the configurations, they are in some cycle. Take an example. Say rule 170. This is the transition diagram. I have shown here. You can see that everyone is in some cycle. So look at this 0001. If you update this, you'll get 0010. Then from this 0010, you can go back 0100. From then 1000, and again you can come back 0001. So it forms a cycle, and all the configurations, they form a cycle. It implies you can start from any configuration. It's a 4 cell. There are 4 cells. So 2 to the power 4 equal to 16 possible configurations are there, right? So if you start from anyone, you loop always, right? You'll be always in cycle, right? So in case of reversible cellular automata, finite reversible cellular automata, so all the configurations are cyclic, right? So 170 is an example of reversible cellular automaton. So what I get, let us consider G is the global transition function. So you see that from one configuration, I'm moving to the other configuration. So there is a function. Suppose, let us consider G is that function, right? So I can consider that some function is walking behind. Suppose this is the function. So I can write mathematically for any x, for any configuration x equal to g to the power kx for some k, right? For this cycle, you can see, if I start from 00, x is 0001, k will be equal to 4 here, because after 4 time step, I can come back here. If I start from 0011, then also k will be equal to 4, because after 4 time step, I can come back. If I start from 0101, that is x equal to 0101, so after 2 time step, I'll come back. So k equal to 2, and so on. So some k I'll find. So the properties here, the transition function G is surjective, right? Surjective means all are reachable, right? So from each for each configuration, you can find that you can reach the configuration from some other configuration. So you have seen in my previous slide, previous figure also, that all configurations, they are reachable from someone else. So G is surjective, and it is also injective. Injective means the one-to-one mapping is there from one configuration. One configuration is reachable from exactly one configuration. So it's injective. So for this reversible, say I can have 2 properties. The G is surjective as well as injective. So when a function is surjective and injective, we call them bijective. So number 1 property. And second is, every configuration comes back in finite time. You can see here, if your system is finite, if your CA is finite CA, you can see that every configuration comes back in finite time. Let us ask this question. Can this second property be true for an asynchronous automaton? That is, here, for example, rule 170 is updated synchronously. So we have seen this kind of discipline kind of things. So all have come back, after some time steps. If we use asynchronous automata, can we see this kind of property? Let us see. Suppose, let us take ECA 170 again. And suppose, say we are updating ECA 170 asynchronously. And so, consider our model is fully asynchronous update. That is, at one time step, exactly one cell is chosen randomly at uniform, and that is updated. And if you follow this one, you'll see this kind of behavior. That is, if you start from 0001, it will reach to 0, 0, 0 or 1, 1, 1. It's interesting. From 0, 0, 0, 1, it's possible to reach all 0 configuration, as well as it is possible to reach all 1 configuration. So it is a total collapse of the previous transition diagram. So I cannot get reversibility, or I cannot see that configurations can come back. So for example, if you start from 0, 0, 0, 1, after some time step, it will go to 0, 0, 0, 0, and it will never come back. It will never come back. So configurations are not coming back. Okay, but this is for rule 170. Question is, well, 170, for 170, I cannot see this kind of coming back property. For other CAs, is it possible to say see this kind of property? See this example. ACA 38. Say, suppose rule 38 I am using. Here in this diagram, I have noted down all possible update. See, on the arrow, on the I have written some numbers, say 1, 2, 3, 4. This means which cell I am updating. Let us consider 0, 0, 0, 1. Suppose I am updating first cell 1. This loop indicates that if I start from 0, 0, 0, 1, and if I update cell number 1, I'll stay in the same configuration. But if I update cell number 3, means this cell, first, second, third cell, and my system will move from 0, 0, 0, 1 configuration to 0, 0, 1, 1 configuration. In this way. So, see, you can observe in this figure, I have noted down all possible update. All possible update. And one more thing you can observe, that from any configuration, if you start, you'll be able to come back to that configuration after some amount of time. So you can see from 0, 0, 0, 1, if you update cell 1, 2, or 4, you'll be in the same configuration. But if you update to 3, you'll go to 0, 0, 1, 1. But from 0, 0, 1, 1, there's a path. So 0, 0, 1, 1, from 0, 0, 1, 1, you can see you can come back directly from 0, 0, 0, 1. So you pick up any configuration. You pick up any configuration, you will find a path. You'll find a loop actually. So you'll find a path to come back to the starting configuration. So therefore, every configuration can come back in finite time. Okay, so yes, it is true. Point number 2 can be true. Every configuration here revisited again and again, and this is actually the one property of reversibility. If we stick to finite system, then coming back to the initial configuration is one indication that system can be reversible. So and it is emulating the behavior, better to say it is emulating the behavior of reversibility. Taking this point, I am defining the reversibility for asynchronous system. Let us call an asynchronous system as reversible if each configuration of the automaton is revisited again and again during evolution. So we are deriving this definition from our previous diagram. So from this definition, by this definition, we can say that ACA 38, which I have just shown, is a reversible one. Well, if I associate a global transition function G with the CA, it is surjective, obviously, because every configuration is reachable. But there was a deviation from the original definition of reversibility. Originally, it was surjective as well as injective. But here, G is not injective, right? This deviation, we are doing here. So G is surjective, but not injective. One more point I can add here. See, since it's a probabilistic system, we have used probability to implement ACA. So ACA means asynchronous cellular automaton. So sometimes ACA can be seen as Markov chain. And from the vocabulary of Markov chain, here, which are coming back to its the configurations which are coming back. So these configurations are sometimes called as recurrent. So in some cases you can call them recurrent, but in our discussion we shall call them reversible, right? Because we are trying to point out the similarity of my system, my asynchronous system, with the classical reversible system. So now there's a theorem, there's a result. There are 46 ACS which are reversible under fully asynchronous update. So our updating style is fully asynchronous update. Fully asynchronous means, let me note it again. It is actually at a particular time step, exactly one cell is updated. And our system is finite system, right? Now, if we stick to the previous definition of reversibility, then I can find there are 46 such asynchronous cell automata which are reversible, right? So obviously I am skipping the proof. So if you are interested to see the proof, you can go to the reference is given, and these 46 ECAs are like this. So here we have noted down the rules. So rule means the local function. By local function we can get a cellular automata. We can get a cellular automaton. So there are 46 cellular automata which are reversible in finite setting. Okay. Very good. So then the question we started initially, that whether a asynchronous system can be reversible, and the answer is yes, at least to some to some extent they can be reversible. If we extract the meaning of reversibility and the derived definition if we use, then I can say some C are reversible. But two examples are given for rule 38, rule 57. We have taken 8 cells. So just experimental result, just to show how they look like, and you can see here that all the configurations they're connected. Okay, very good. But there's a point. Point is, see, reversibility refers to a phenomenon which allows a system to go back. So backward transition should be allowed, right? But the definition which we have given right now, that does not deal with the backward transition. We can go forward only. So the question may come, well, the definition might work, but that cannot be reversible in classical sense, because the all ACAs, they are not injective. So if I am asked, is it really possible in asynchronous system? From one configuration, I can go backward. Take this example, rule 38. Just now we have given example, and we have claimed that rule 38 is reversible. But see, suppose I am reaching 1000. This 1000 can be reached from 1100 and 1000 by updating cell number 2. So even if I know that which particular cell is updated, then also I cannot uniquely determine my previous configuration, right? Suppose I am given 1000. I know that 100 can be reached from 1100 as well as 100, 100, 1000. Both are by updating cell number 2. So even uh, uh, this cell number 2 is given, that then also I cannot uniquely determine my previous configuration. And reversibility was, it should allow a system to go backward. So I cannot go backward. Now at this stage, I want to ask this question again. Well, if that behavior is mandatory, can we get this kind of behavior even in asynchronous system? Let us take this example, ECA 57. See, note that all the update is fully asynchronous update. That is one cell, exactly one cell is chosen for update. See, in this example, I have started from 0, 0, 0, 0. First cell is updated. System goes to 1, 0, 0. Fourth cell is updated. System goes to 1, 0, 0, means remains in same configuration. Third cell is updated 1, 0, 1, 0, and first cell is updated 0, 0, 1, 0. That is, you see that some one-to-one correspondence is there. An interesting point is, if you want to go back, yeah, you can. If you know that which particular cells are updated, right? And if you again apply rule 57, you can go back. That is 0, 0, 1, 0. If we update first one, you'll get 1, 0, 1, 0. From 1, 0, 1, 0, if you update cell number 3, you'll get 1, 0, 0. From 1, 0, 0, if you update cell number 4, again 1, 0, 0, and finally you'll be able to come back 0, 0, 0, 0. So, although for ACA 38 or rule number 38, I cannot have that injectivity property. I cannot go backward after knowing the which cells are updated, but in case of 57, it's possible. In case of 57, it is possible. And this behavior is closer to the classical definition of invertibility. Right? I can go backward. And yeah, there are such asynchronous systems, asynchronous cellular automata, where we can observe this kind of behavior. So, we are working with ECA only, and in ECA rule space, we can find 16 ACS where backward transition is possible under fully asynchronous update. Right? So, in our first definition of reversibility, we have identified 46 ACS which may not follow the injectivity property, and where I may not go backward. But from that 46 properties, some ACS are there where this backward transition is really possible. So, this is an important development, and we are much closer to the classical definition of reversibility. And these are the 16 ACS where this backward transition is possible. Okay, so we have shown evidence that in case of finite system, if I consider the definition of reachability from itself, there are asynchronous cellular automata which can do that one. Now, if you want backward transition property, this theorem tells you, well, there are some ACS which can exhibit the backward transition property. But still, you may ask question, because we have started our discussion for finite lattice only, and cellular automata classically defined over infinite lattice. So question comes, well, it may work for finite system, but will it work for infinite system? Now, if I move to infinite lattice size, then there is no guarantee that if I start from initial configuration, for one configuration, it will come back. It will not come back. It will not come back. And cyclic property is not essential to be reversible for infinite systems. Now, question is, if my cellular automata is infinite, defined by infinite lattice, can we, get this kind of property, reversible property? For that, let us define another term called phase space invertibility. It's like this. Suppose rule 38, which is the injective we have just shown. And suppose my initial configuration is infinite. I mean, say 0, 0, all 0 left hand side, all 0 right hand side, and middle 2 ones. And suppose red marked 1 is chosen for update. So it moves to this 0. So 0, 0, 1, and all 0. Right. So in this way, it can move. Now, interesting point is, if you apply 54 over this new configuration, so 0, 0, 1, or 0, and you update the same cell, right? Say 0, the red marked 1, underlined red marked 1, and we can see that, well, my starting configuration has come back. That is 0, 0, 1, 1, 0, 0. Right? So two rules, if we work together, they can work together, then I can come back. So in that sense, if 38 is my f, the forward rule, 54 is kind of, to some extent, I can say it's the inverse of that one. So inverse of the 38, right? Now, if I can get such pairs, 38, 54 like this, I can say, yeah, it's possible. And then I need not to look at the point whether the initial configuration is coming back or not. So let us define this one, the phase space invertibility. Right. So an ACA is phase space invertible if there exists another ACA such that if X is the next configuration of Y for the first CA, then Y is to be the next configuration of X for the other CA. In this case, in this example, for 38, X is my 0, 0, 1, 1, 0, 0, and Y is 0, 0, 1, 0, 0. For 54, the reverse one. I start from Y 0, 0, 1, 0, 0, and its next configuration is 0, 0, 1, 1, 0, 0. So actually, the configuration space is invertible. So one configuration space, another configuration space, as if the arrows are inverted. The direction of arrow is just inverted. And this is the actual definition of reversibility. Right? From one configuration, if I go to other configuration, then by another function, by the inverse function, the arrow should be inverted. That is, I can go backward. Right? So my first definition is to come back by forward moving only. Here there is no need of move forward and and then wait for coming back. Here I am saying, if I can go from one state configuration to other, for any pair of this X and Y, I can have the pair Y and X. And if it works for all possible such pairs, we call the first one as phase space invertible. So I claim that this definition is more close, the classical definition of, reversibility. And obviously, the backward transition property, all SES with backward transition property, just we have shown those there phase space invertible, because we have seen that using 57 rule I can go forward, and using the same rule I can go backward also. So so all the rules having this backward transition property, they are phase space invertible. Yeah, there are 40 SES. There are 40 SES. These SES can be defined over infinite lattice, not for finite lattice only. There are 40 SES which are phase space invertible under fully asynchronous update. So to see the proof, you can go to the reference, and these are these SES. So we have seen a set of 46 SES. Here we are seeing set of 40 SES. See, actually the same one. I mean, this one is the subset of the previous one. Here 6 SES are missing. Right? Here 6 SES are missing. So by the original definition of reversibility, which we have defined for asynchronous system, and this one, they are very close to each other in that sense. However, this definition, as I've said, is more close to the classical definition, and here finite lattice size is not mandatory. I can use infinite lattice. So all these things, all these results show that by reversibility we mean something. To achieve those property, to achieve that goal, these are mandatory. The system is to be synchronous always. For the asynchronous things, asynchronous systems, we can, we can observe similar behavior. There are other results. See, all the results I have shown, they are based on the fully asynchronous update, and all this behavior, they can be observed. They are observed in alpha asynchronous cellular automata also. That is, they can be reversible, they can have some backward transition property, they can be phase space invertible. Some results are known. I have not presented all the results. You can find the references and find the results from the given references. Some results are yet to be finalized. But the point is, for alpha synchronous update, same kind of behavior we can get. And another point, that in my examples as well as in the theorems, we have taken only ECA rules, only binary systems. For the other systems, for non-binary systems, means for non-binary automata, we can have same kind of behavior. Let us define a new term here called self-timed cellular automata, STCA. This is another view of asynchronism. This is actually another way of implementing asynchronism. See, cellular automata is a mathematical model. To model independence, we have used probabilistic update. And STCA, it says, well, you use different clocks for different cells. So therefore, a cell is self-timed. It has its own clock. It runs by its own clock, right? It does not, share the global clock, right? So if I'm having n number of cells, I'm having n number of blocks. So these cells are self-timed. So it is again another way of implementing asynchronism. And Lee and his colleagues, they constructed in two-dimensional self-timed cellular automaton by embedding Morita's rotary element. In our last lecture, in last Saturday, Morita was talking about partition CA, and he used the rotary element, his famous rotary element. These rotary elements are reversible elements, and if we construct a cell automaton by using these rotary elements, so my cell automaton remains reversible, because the rotary elements itself are reversible. So since I'm constructing STCA by embedding this rotary element, so my finally the CA remains reversible. And interestingly, the scheme is not limited to finite only. Theoretically, they can be infinite. So finiteness is not associated with this implementation. So this STCA, self-time cellular automata, they are reversible, and they can perform some reversible computation. Okay, I'm about to conclude the discussion. So we have shown the evidence that asynchronous systems can show reversibility. It is not that what synchronous system can do, asynchronous systems cannot. At least for the reversibility case, if we extract the actual meaning of reversibility, the implication of reversibility, we have seen that, well, asynchronous systems can show also the reversibility. In fact, asynchronous cellular automata exhibit a range of rich behavior, which synchronous cellular automata cannot show, right? So, it's richer. The behavior-wise, asynchronous cellular automata, they are richer than than the synchronous cellular automata. I can give one example that asynchronous cellular automata, they can show the cloud behavior. You can if you're interested, you say where. So we have shown that the cloud-like behavior, the configurations can show for the asynchronous cellular automata. So combining all this, I can conclude by saying this one. That's really independence drives excellence. If the system is independent, if the system has freedom, the elements has freedom, and if it is democratic, so it's democracy, the independence, it is true that the statements I'm making, they're true for society, true for the computing system. It can always perform better than any kind of autocratic system. So independence drives excellence. Last but not the least, I have to what I have said, what I have presented here, credit goes to my students mainly. So Vishwanath Sethi and Shovik Roy, they did PhD on cellular automata, asynchronous cellular automata. Shovik also did his master's work on asynchronous cellular automata. Apart from these two scholars, Anindita, Krishna, and Shubroto, they also did their master's work on asynchronous cellular automata. So the results I have shown here, many of the results are done by these students, and I have to specially thank to Nazim. Nazim is my collaborator. Is our collaborator. He was associated with almost most of the works of reversibility. So thanks to Nazim. So thank you. And last word. So there are many interesting things, many properties which we can observe in the asynchronous cellular automata. It's a many things are yet to be explored. So it's an open field. So if we come together, if we work together, so many excellence, many good behavior, many rich behavior can be observed in the domain of asynchronous cellular automata and asynchronicity in general. Thank you for your attention.
Thank you, sir, for your wonderful talk. So now it's the time for question answer session. So if you have any question, please ask.
So I have a question. Thank you very much, sir, for such a nice presentation. My query is that do we have a classification available for the ACA as well, somewhat similar to the Wolfram classification, wherein the classification is made on the basis of the level of the reversibility shown by the ACS?
Sorry, I missed that one. Could you please repeat?
Yes. So is there a classification available for the ACA as well, and wherein the classification is made on the basis of the level of the reversible properties shown by the ACA, somewhat similar to the Wolfram one?
Yeah, this is the classifications available based on reversibility, based on recurrence property, based on the convergence property. In a recent work, Shubroto and Shovik, they in 1 year back maybe, they have one work where they have shown that some systems, they are they can show reversible behavior, convergent behavior, and interesting behavior. And Shovik and Shubroto were exploring that that they can show the class transition, the transition behavior. So what you are saying that this kind of classifications available for asynchronous C also, and as I mentioned, some additional behavior we can observe here.
Okay. Thank you, sir. I have one more query that,
Please.
I mean, for what purpose do we study reversibility? I mean, what purpose is solved by if we come to know that something is reversible?
Yesterday, Professor Sushmita Shurkole was talking about reversible gate design. So one reason is of using this kind of application, reversible circuit design, etc. This is one application where you can use reversibility. This is one example. Apart from that, see, if you look at the finite CA, finite cellular automata, one example I can tell you right now that, say, for example, random number generation, many people worked on this, and for that they have explored, reversible system. Although for the randomness, for example, Wolfram used 30 rule 30, which is not reversible. But many researchers, they have explored reversible CA for the purpose of PRNG, random number generator.
Thank you. Thank you so very much, sir.
As well as cryptography. For cryptography purpose also, reversible CA were used.
Yes, that could be the potential use. Thank you, sir. Thank you very much.
So I have two questions.
Mm.
The first question is, so you have concluded that independence drives excellence.
Mm.
Following that particular quotation, independence drive excellence, and that is the conclusion part. And you have started with democracy and connection of democracy with asynchronism. So obviously, when we are talking about synchronous system, there is no independence. But if you want to model societal phenomenon, in society also there are independence, but there are some local level centralized behavior. We have to follow some societal norms and all these things. So if you compare synchronous, then as independence, and then too much independence sometimes drive towards too much chaos or something like random. So how to model society with asynchronous cellular automata by following that trade-offs. So what I'm trying that if in that one side is synchronous and one side is too much independence. That is everyone is following their own wish, and it sometimes may drive towards randomness and chaos. So how to trade off this thing? This is the first question. And the second question is, uh, if you consider the implementation of alpha asynchronism, so each and every there is one centralized, there is no centralized clock. However, in alpha asynchronism, when you are really implementing alpha asynchronism, it depending on some randomness, and based on the randomness, the cells are updated. So it somehow gives us a feeling about independent clock for every cell. So if we consider the finite instant, then how it is different from self-time cellular automata? Because I can understand that alpha asynchronous only give us a favor of that independence, but in self-time cellular automata, the clocks are associated with each and every cell. But something like if you can compare these two things like pseudo randomness and randomness like that. So how to distinguish these things, two things for finite cases and beyond, what are the exact differences we can get or something like. So if you just elaborate a little bit.
Okay, the first question is, independence, the trade-off, independence, freedom, and discipline, and the rule, etc. See, when I'm talking about cell automata, cell automata, the cells are arranged in the regular network, and the cells are allowed to interact with its neighbors, and finally, cells have to follow some rule. So, cell automata are mathematical modeling tool. It's a mathematical tool. And this is independence means I'm not allowing the cells to go beyond the lattice size, right? And something is fixed. What is fixed? Some norms are fixed. The example I have shown here, it's a rule 170. See how to act. So when 000 is given, it is to be 0. So some rule is, some rules are given, right? So if I have understood your question properly, independence is here, in case of centralized system, some central clock is there. So all cells are forced to update their states, right? But in case of asynchronous CA, only one point. That okay, you can update your cells, update your state, at any point of time when you wish. It's not that update whatever you want. At least the automata I have mentioned, the model, I have discussed in this talk. So rule is there, and only cells can update it independent of the time global clock. So it is not that it is not the cells are not following any particular discipline, any particular anything is not discipline. Some rule they are following, but the dictation of others always that you do this at the time that particular is relaxed. So what you have said, that is actually followed at least in asynchronous cell automata, which model I have discussed here. So that thing, as per my understanding goes, that I have said here. There is the first question, and for the second question, as per my understanding goes, probabilistic update is actually mathematical way of representing the implementing independence, right? I have said the cells are independent, but how to implement that one? See, if you simulate this one, or if you simulate, finally you have to simulate it in some computer, right? So again, centralized system is there, right? So centralized and synchronous system is there. So how to implement how to model that one. So one way is you use the probability. This is not the only one. This is not the only one. So many people has have argued that okay, this is a good way of implementing independence. Someone may argue no, may disagree. No, this is not the good way. Yeah, but it's one way of implementing independence of cells. On the other hand, self-time, cell automata, here from implementation point of view, suppose I want to really design some circuit, some hardware for that. So how to implement that alpha synchronous system? Not possible. For mathematical purpose, I can use alpha synchronism. But if I am asked to really implement that cell automata in hardware, say, right, then self-time is a good choice. You give, you allow some cells, allow clock for the individual cells, and they will be governed by their own clock. And in the paper I have cited the Morita's paper and Lee Morita, they have claimed that even if I want to do reversible computing, and your power consumption will be less, because if there's a global clock, so global clock is being implemented, and everyone is following that one. And if the local clock is there, the power consumption is more efficient from implementation point of view. So one, I think alpha synchronism is the mathematical way of representing the independence, and self-time is really one implementation, direct implementation of asynchronism. Yes, Shovik.
Yes, thank you.
I think Preeti, Shumita Madam, Shubroto they have some questions. So please ask one by one. Shumita ma'am.
I have two questions. One is that, am I audible?
Yes.
The first is that here the independence have been measured by this thing, the probabilistic update, right? In the model that was discussed today. I just want to know, is there any model where there have been a fuzzy update, or is it has it been explored?
Fuzzy cell automata are there.
Fuzzy CA is there, but I mean this updates, if it's measured by this probabilistic update, right? Is there has there been any work in this area?
No, at least I don't know. Apart from these two updates, there are several other types of updates, other types of asynchronism. For example, beta asynchronism and delay sensitivity. These things are there.
Okay.
Sometime apart from alpha, some alpha 1, alpha 2 for different cells, different probability also assumed. And sometime instead of considering any alpha, suppose there are S number of cells, I am taking a subset of that cells. In each step, I am finding the subset, and based on that, I'm updating. These things are there. These works are there.
Okay.
But I have not observed this work. What you're mentioning, that fuzzy update for this case.
No, it is just my question. I was just thinking, and another thing is that when this is independent, I mean one cell, you are considering one cell.
Right.
Have it been also modeled by if there are two cells, which has such which are suppose two cells are changing, then is there any work on that area?
Actually, one cell and two cells, I mean, if the cells are not consecutive, then the result will be same.
Yes,
Suppose,
if they are not consecutive,
then the same result.
okay.
Right? Means the properties called atomicity property. If the update is made following atomicity property, right? In case of ECA, if I update first cell, then third cell, then fifth cell, then seventh cell consecutively,
like
then no problem.
this.
Same problem. We understand that first cell, then fifth cell, then third cell, or first cell, third cell, fifth cell simultaneously, the same result, same behavior we can observe. So dynamics wise, behavior wise, we'll see the same thing, right? So therefore it is a similar similar result we can get, beat convergence, beat reversibility, same behavior. And if I consider alpha synchronous behavior, alpha synchronism, so then two cells can be updated simultaneously. That is different. So therefore, fully asynchronism and alpha synchronism, they are not same, because here two consecutive cells can get updated, right? Whereas in fully asynchronous case, the two cells cannot be updated. So they are two different.
Okay. Thank you.
Thank you.
Thank you for this.
Yeah, Shubroto has.
Yes, sir. Sir, my query is on that quote-unquote statement that universe is a big cellular automata. So I'd like to hear your point of view that if this is so, I mean, if I believe that this is a huge cellular automata, then which class of cellular automata that can fit exactly the universe? I mean, the universe belongs to which class of cellular automata? It is been asynchronous or else?
I don't know. So this is the proposition of Edward Fredkin.
Yeah.
So after some time, Norman Margolis will join us, and he is a student of Fredkin, and ask this question to him. But I just, I'm just, I know this one is a statement of Fredkin, that he believed that it's a cellular automaton, it's a computer, the universe is a computer, it's a cellular automaton, and I have no comment on this. I have in my slide I have used this word. But if it is yes, it's all right. Even if it is not, then also we can see that by cellular automata we can model, many physical behavior, many natural behavior. So it's a nature inspired model. Okay. So that point actually I have made, that comment I have made. So on this point I have no comment.
Yes. Okay, so then, sir, I have another query about that democratic and autocratic class. I mean, if we implement in a real time scenario, if you try to implement that using that asynchronous cellular automata, then what about the handling of outer perturbation or noise? I mean, is this I mean changes the class of the cellular automata if some noises abruptly come to that system? I mean, সবকিছু তো ঘেটে দেয়।
Sorry, not clear. I mean, please repeat the question.
I mean, if we try to implement some real time scenario using that asynchronous cellular automata, and we know that in real time there is a huge noise and perturbation is there, then how you I mean, if there is a outer perturbation came during the simulation, then is that perturbation changes the class of cellular automata? I mean, there is only two class, synchronous and asynchronous, or the synchronism absorb that perturbation. I mean, able to absorb.
There are some results that behavior of synchronous CA can be modeled by asynchronous CA. So they are synonymous. Computationally, what asynchronous CA can do, synchronous CA can do the same thing. These results are there by changing the dimension, by changing the states. This is a old result actually. So old result that I can do. So whatever you can do by synchronous cellular automata, you can do the same thing by asynchronous cellular automata. But thing is that you are saying that change of synchronous to asynchronous. See, synchronous system is one system where, so for example, all the cells are guided by the clocks, right? So then how can you read off that clock? But your answer may be yes if you start from alpha asynchronous CA. See, you think mathematically, alpha is every cell is allowed to update itself with probability alpha. So if you make alpha equal to 1, it becomes synchronous system, right? So you can say that asynchronism is a subset, subpart of, subclass of synchronous, synchronous system is subclass of asynchronous system where all the cells are updated simultaneously. That much you can say. Okay. It's all that, Shibpur?
Yes, sir.
Yeah, Shupriti, yeah.
Yes, sir.
Hmm.
Actually, I wanted to know that does the properties of CA change if we change the value of alpha in alpha synchronous CA?
Yeah.
And
What kind of property? What kind of property you are?
like say for sir, for example, I get a chaotic CA in for some value of alpha, then I change the value of alpha. Then for the same rule, I can get different type of property. I may get different type of property. The CA may not be chaotic. Or or I can say, as you said, that rule 38 shows reversibility in case of asynchronous CA. But suppose, sir, if it is alpha asynchronous CA and I change the value of alpha, then even if the rule number is 38, I may not get this reversible property in that CA. So, is it possible, sir?
Yeah, it's possible. It's possible. See, these works are not yet finalized actually. You know, many things are to be done. Not yet finalized. It's possible depending on value of alpha.
So only for a fixed alpha, I can say that this rule shows this type of property. When I say about this for this alpha asynchronous CA.
Maybe we have to. So, for example, alpha equal to 1. Let's
Yes,
say
in
alpha
that
equal to
case,
1.
I can say that this is synchronous CA.
Right.
But apart from the value 1, for less than 1, I may not accurately say that this rule will always exhibit chaotic behavior or reversible CA.
Behavior should change.
Yes.
But how they are changing, that are to be explored.
Okay. And sir, second thing that I wanted to know, that for infinite and finite lattice also, just I want to know that I am just guessing that the property should again change. For example, sir, suppose that you said that rule 170 shows reversible CA. For synchronous CA as well, it shows reversible CA. But when I come to this infinite lattice of cells, in that case, it is a shift rule. And it continues shifting infinitely, so we will never get it back. So it may not be the reversible one.
No,
So
170 is reversible, because irreversible is, the definition I have given for the finite case only. The question comes into picture if the system is finite, and then only system can come back, right?
yes,
Then only the system can come back.
so we cannot right now define this reversibility for this finite lattice, infinite lattice, right, sir?
No, the reversibility we are referring here. So the finite case, there's a derived one, na? Reversibility is that I can go back, right? I can go back in reverse direction. So even 170, it is shift rule. Say from one configuration is given, uniquely from which configuration it has come, right? So you can go back. There's no loss of information.
Okay, so in that case, for infinite or finite case, we may say that the property remains same. But for this, okay, no, sir. Now I get this. I get this. Okay, thank you, sir.
Sir, one question in the chat box also from Shivaraj speaking.
Yeah, just let me see. Can such reversible scheme increase? Shivraj, you have written that can such reversible CA increase the efficiency or accuracy of current computation? I'm not understanding the meaning of this. Accuracy of current computation means, and second question is, we don't have reversibility in macro level phenomenon, but it is observed in micro level. Similarly, can we have an overall synchronous CA computation? Can we have an overall synchronous CA comprised of many reversible ACA? Well, Shivraj, that I have just said that one point, one result is old result is there, that asynchronous CA can emulate the reversible CA by increasing dimension as well as or by increasing the number of states is possible. But you are saying that overall synchronous system can be comprised of many reversible ACS. I don't know what you want to mean here, right? But self-time CA maybe the answer of your question. Self-time CA at individual cells, they are self-timed. They have same they have same clock. Based on that, following the merging all such elements, I am getting the final CA. That might be your answer. Okay, Shibaj is here. I don't know whether my answers satisfied him. I don't know. Yes, Sukanta.
No, sir, Shivraj is not here. So any more question? Sir, I have just one question. Phase shift invertibility, you mentioned about this, and you mentioned about two rules, 38 and 54. So is it kind of non-uniform CA?
No, not non-uniform. I mean, it's asynchronous. So all the cells are using same, same rule.
So any more question? So, sir, can we go for the next session? So then I would like to call Kamalika to host the next session.
Thank you. Thank you. Thank you all. Thank you for attention.
Thank you, sir. Thank you, Shukanta. Okay, so